Hi, my name is Bernard Brault, and this is a follow-up of a series I'm doing about light, photons, radio waves, and from a quantum mechanical approach. So this is part two. In the first part, I scared you a little bit, and I showed you the math behind it. But in the end, it was not too scary because what came out at the end was that if you have a photon that has a specific energy value, and that means that it's an energy eigenstate with very specific energy, that this state evolves in time, and the way it evolves in time is just that it gets multiplied by a phasor. So it doesn't change its magnitude, but it just multiplied by a phasor. And what turns out is that if two possible states actually combine, then the phasors can cancel each other out if the arrows are opposite direction. So let's go back to where we left off, and I left off with the double slit experiment, which is shining a let's say a red light into two slit that are very close to each other on a film, and you project the image far away on a screen, and what you see on the screen is you see an interference pattern where light becomes very bright at certain location, very dark at other location, and then bright and dark and bright, and you see this pattern. What's interesting is that you could actually send one photon at a time, right? And if you only send one photon, you're not going to see this pattern. What you're going to observe if you only send one photon is that photon is going to hit the screen in one specific location. And that location is most likely going to be on one of these bright spots, and it will never be in one of those dark spots. In fact, the reason why the dark spots are dark is because photons never hit that specific location. And quantum mechanics gives you a way to calculate the probability of where it's actually going to hit on the screen. And this is a probability density wave, and where it's zero, photons never hit that spot, and where it increases, the odds are, that it's going to hit there. You cannot predict where it's going to hit, but you could predict with incredible precision the probability of where it might end up, right? So this probability function here you can calculate with extreme precision. It's probably one of the most precise theory that we have out there. So let's go into the double slit experiment and look at it from the quantum mechanic perspective and these phasors and so on. So light can take two different paths. Even though you're sending a single photon, there's two possibilities, and if you have two possibilities, a combination of the two possibilities, actually if you have multiple possibilities, a combination of all the possibilities are possible. And then what you need to do is look at the contribution of each possible path and add up their amplitude, and you square the amplitude and you get the probability. In this case, you could go through the top. One probable path is this one, and I'm looking at what is the probability it's going to hit the screen here at distance 10 centimeter above the middle, right? So you got here's the center of the screen. This is 0.1 meter or 10 centimeter above, and the top path has a magnitude here. The phasor arrives this way. Keep in mind, as it traveled here, it was just spinning around like crazy, right? It went around like a couple million times. I said it spins around 1 time per micron, so that's 1,000,000 times per meter. If this is several meters down, then this thing is spun around like millions of times. So eventually, when it hit the screen, you had, let's say, for example, this angle right there, and the bottom slit on the other end arrived, the path there takes a little bit longer. And because the path takes a little bit longer, then the bottom one will arrive with a different angle, right? So if you compare the two here, it's this one here, and the bottom one arrived a little bit later. And if that path had been longer, so for example, if the bottom slit had been a little bit lower, then this arrow would have spun a bit more, and it might be there. But right now it's right at this location, so you add up the two arrows right there, and as you can see, they're somewhat contributing, right? So they're not, this one doesn't cancel the other one out, and you square their magnitude, and then you obtain a certain value right there. If you do it a bit lower, if you do it at this location here, what you'll notice is that at this location right there, the two magnitudes or the two phasors are opposite of each other. And that's why when you add up those two arrows, they cancel out each other and it becomes 0. And the square of 0 is 0. That's why you have no chance that the photon's going to hit this spot. And that's going to be like a dark spot on the screen. Moving further down, you're going to have other locations like this one, for example, where the two possible paths will arrive with arrows pointing in the same direction. And because they're pointing in the same direction, that's the maximum that they can add up. So they doubled in length, and because they double in length, they quadruple in probability. So this is why this is a very, very highly probable place, and this would become like a bright spot. So what I ended up doing is making this, calculation for each one of these points here. At every millimeter, I calculated the path and the angle of the two phasors and added them up to eventually come up with this probability function. So let me show you this. We're now in Excel, and this is the top of the screen. X is 0.1, and as I'm going down here, basically going down to the screen, middle of the screen, position 0 is right there, and then you go all the way down to minus 0.1. So for every position on the screen, what I do is I calculate the length of the first path, the length of the second path, and then I rotate this phaser around. This crazy rotation gives me like a huge number in radians, which corresponds to millions of times going around. I do a modulo 2 pi just so I know at the end. I don't care how many times it's spun around, I just care where it lands, where that arrow lands after so many spins, and this is where it lands. And in order to calculate the magnitude and add up the arrows, and these arrows are actually complex numbers, I need to add up the real part, the imaginary part, and then square them up, and I get this probability right there. So at x equals 0.1 on the top of the screen, I get this probability that you see right there. And this is a number that you see right here. 0.1 has this probability. And as I'm going down on the screen, you see there's location here where it's going to be dark, and this section is going to be bright, and this section is going to be dark. So all of this here was calculated, and this is the probability right here for every position on the screen, every point, every 1 millimeter. What's interesting is this was done for red light. If I were to change this to blue light has a different energy and spins around much faster. And let's turn this into blue light. It's about 450 nanometer. And what you'll see here is that you have the interference pattern is slightly different. I'll get into white light eventually, or other forms of functions, but what you'll find out is that if you take something that's a combination of different light, what you do is you calculate each combination and you add them up, right? That's just the way it is in quantum mechanics. You add all the possibilities and so on. One thing that's missing is that in the actual experiment, let's go back to red light here, 750 or so, is that the middle section, right? There's the spot in the middle that's supposed to be brighter, and this one's supposed to be dimmer, and that's not what I see right here. So I must have missed something, and if you go back, I'll show you what I missed. So going back to the experiment here, so there's actually going through the top slit here. This slit is not infinitesimally small. It's not like it has a certain amount of a certain gap to it, and what that means is if I amplify this and look at it, in fact what I have is that there are multiple paths, possible paths going through the top slit, not just one but several of them. And if I want to be very precise, I would try to draw hundreds of these paths and calculate hundreds of these phasors up here. And what I did is I did 6 for the top and 6 for the bottom. And notice the reason why this is more precise is because obviously the top one up here, the top path there, the fastest one, and the one at the bottom down there will be very close, but the phaser, depending how wide this is, the phaser for the bottom slit there is going to be slightly out of phase because it took a little bit longer to go through this slit. Not compared to the bottom one that's much further down, but still longer. So what I'm going to do here is I'm going to divide this into 6 different possible paths for the top slit, 6 different possible paths. I'm going to end up with 12, 6 plus 6, 12 phasers. I'm going to add up all the arrows and calculate the probability. So let me show you what that other calculation looks like. It's a lot more involved. So now I'm still starting at point 1, and instead of having through the first slit only a single path, I did 6 of them. So L10 to L15, 6 paths through the bottom. Finally calculating the length of each one of them, the 12 paths, and the rotation, how many radians around, and then eventually all the angles. And when I get to the total real there, as you can see here, I'm adding up all the real value for the 12 paths. I'm calculating all the imaginary values for the 12 paths, square up those numbers, and this is the probability that I'm getting. So 2.29 right there, and that corresponds to 0.1, or the top of the screen. Notice that normally, the probability here you might recognize doesn't make sense, 140, because the sum of all the probabilities have to be equal to 1. So I did not go through, if you want, normalizing this to 1, but because I didn't feel like I needed to. But in reality, if I want to make this really a probability, I'd have to normalize this. But what's interesting is now it's more realistic. The middle spot is more probable than these lobes here. So you still have these different lobes, but you know what? They sort of fade out, and they fade out because there's a certain amount of gap. And of course, if I change the frequency, I'm going to get something different. If I go to 400, for example, and it's going to be blue light, let's take a look. You see blue light just has more lobes there, and let's get back to red light, 750. And it's just a bit different, right? Since I did all the calculation for both slits, 6 at the top, 6 at the bottom, I said, why don't I just block one of the slit and calculate what's going to happen if it only goes through, let's say, the top slit. So this is the probability of all the 6 different waves going through the top slit. And what you see there is that light does not just arrive at one location, but it's sort of spread out. And the narrower the slit, the more spread out this will be, and that's very well known. Photographers know this. It's called dispersion, and it happens when you actually reduce the aperture of your lens. If you go to this very small aperture, f22 for example, and they don't dare to go much smaller than that because the image gets too blurry. But the reason for that blurriness in the image is because light starts spreading out. And talking about the light spreading out, let's go back and take a closer look at this, right? So if I look here, and if I make this slit there very narrow, right? So keep in mind that this thing spins around 1 full circle per micrometer. But if I make this less than a micrometer, for example, or something extremely small, what's going to happen is that whether light goes through the top of the slit or the bottom of the slit, it will arrive here at every single point with the same angle. There won't be any difference in the phasers. And the reason why there won't be any difference in the phasers is because it takes the same amount of time, because the time it takes is a distance here, and it's the same distance going through the top here or the bottom. Mind you, if this thing was spinning much faster, like a gamma ray for example, then of course we wouldn't have this. A gamma ray would show up right here in the middle. But because the frequency is relatively slow compared to the actual opening of the slit right here, what we end up having is light dispersing. So it's kind of interesting to see that initially you think that the laser beam goes through a straight path and then hits most likely the middle right there, and that's true, except you you don't think that it's going to spread out, and the spreading out is not because it's hitting the edge of this screen there or the edge of the slit there. It really has to do with the fact that, you know, there's no cancellation on some of the other possible paths, right? So let's reopen the this up, and like if it was a lens. And in my next video I will describe what happens, and then we'll create lenses and things like this. So we're going to put imagine that this is like a camera with a decent let's say 2.8 aperture, and this is like a sensor behind the camera or something like that.